Okay, number 3. We can solve this over here whichever you want to. I usually solve for R2 first, even though it's not listed. But you can solve for R1 and you use Kirchhoff's law to solve for R2. Either way you go. Well, R2 is the one that actually sets VB. Of course, it can't set VB without R1, so that's usually just the one I solve for first. You can solve for R1 and then use Kirchhoff's law to solve for R2, or you can solve for R2 and then use Kirchhoff's law to solve for R3. It's whichever route you want to go, right? I mean, you don't have to do them in the order they're listed. You do them in the order that's just the way I do it. Because there's 2 answers that deal with this guy right here, VB, right? You understand? So that's usually the one I solve for first. But like I said, it don't make any difference. So VR2 would be equal to 1.8K. Of course, the K is going to cancel out. Divided by 11.8K. And the K cancel each other out. And we'll multiply that times 10. And what does that give us? Okay. VR1 would be equal to 10 minus 1.5 using Kirchhoff's law. Like I said, either way, you should get the same answers. And what do we have here? Yeah, 8.5 volts. And then, of course, this is equal to VB, and that's just why I do that. So, right? Okay. So now we can solve for VR4. So VR4 would be equal to 1.5 minus 0.7. 800 watt? Can be 800, because that's fine. Okay, 800 millivolts. You round it? Are we okay? And then IE, which is equal, we're going to assume is equal to IC, right? Even though they're not, would be equal to 800 milli divided by 200 ohms. What does it give me? 400, huh? 104 milliamps. Are we okay? And then VR3 would be equal to 1K times 4 milli, which would be equal to 4 volts, right? Then VC would be equal to 10 minus 4, so that's going to be equal to 6 volts. Voltage collector to emitter would be equal to 10 minus 6 minus 0.8, right? So what we're doing is Kirchhoff's law again. So I know the voltage drop across here. I know the voltage drop across here. And what we're trying to calculate is the voltage drop across there. So what we got? 5.2 volts. I guess that's everything except for AV. So AV is going to be equal to approximately 1K over 200 ohms, which would give us 5.5. And AV has no units, right? Because it's a gain. Well, I know this is what's applied to it. It's Kirchhoff's law. So if I was to come up here and draw a series circuit with 3 devices in it, I have no idea what that one is. It's a rheostat, right? You understand? And then I come back here and I apply 10 volts to this thing. And I give you the voltage drop here. I say, okay, this guy's dropping 4 volts. This guy's dropping 0.8 volts or 800 millivolts. What would be, according to Kirchhoff's law, and this is 10 volts over here, this guy, the sum of these voltage drops have to equal to what? 10 volts. So how would I find the voltage drop across there? That's not 800 volts, that's millivolts. Well, I would say, I would say 10 minus 4 minus 800 millivolts. 10. Wait a second. This is 6. I'm sorry.
10 minus 6 minus 0.8 is 6 minus 0.8 is 5.2. That kind of confusion right there.
10, which is the applied voltage, minus the voltage drop across this resistor, minus the voltage drop across that resistor. I don't know what you're saying, Joe. Well, I didn't come up with an answer. I just wrote down what y'all gave me. It's 3.2. So I understand now. I mean, I just wrote down the answer somebody threw out. And even though I should have known it, because 10 minus 6 is 4. Well, no, but that's not what you said. You said, where did the 10 come from? So I understand the answer was wrong, but the way you asked the question wasn't right? So you were right, but the way you asked the question was wrong. So you know where the 10 came from now, right? So you're right, but like I said, I should have known that was wrong in my head. Why?
10 minus.
Yeah, just 10 minus 6 was 4. Well, I should have known 5 should have been wrong.
I was wrong too.
I mean, you can use, if you're, I don't know how the formula in there is given, but still, this is just watt. I mean, this is one that you shouldn't really have to use watt. Well, not you're gonna have to use a calculator, but the only thing that we're going to do is what sets the voltage here. So all it is VB minus 0.7 if it's a silicon diode, and that's the only thing that we're concerned with. That's a little different than what we learned in DC, right? And that's what's so cool about these guys. These guys actually give us a gain. So. Now understand, these guys don't create power, these guys just manage the power that's already there, right? You understand? So when we talk about gain, it says, okay, if I put 200 millivolts in peak to peak, then I'm going to get 1 volt out, right? You understand? I'm sorry, we'll get the times 5. 100 mil, so we get 500 millivolts out. But we're not creating voltage, we're not creating power. All we're doing is managing the power that's available from that DCT up there, right? You understand? So a lot of people think these guys create power. All they do is manage the power that's available. So we get a voltage gain out of this. If we get a voltage gain, then odds are we're going to get a current gain. If we get a current gain and a voltage gain, then of course, what type of gain are we really shooting for? We're shooting for power. So we're getting more, relative to the signal, we're getting more signal out than we're putting in. And we never can get more power than is available from this guy right here, right? From the power supply. And that's why we call it a power supply. So is there everything okay?
Yeah, I missed it. But I understand.
You did?
Yeah, that's why I asked. So I had subtracted 6 minus 0.8. Came out with the 5.2.
Okay, I understand, but you got to understand it's the voltage drop VCE is what? It's the voltage drop across the transistor. So what is the voltage drop across the transistor? Well, we know this guy and we know this guy right here, right? You understand? And so it's nothing but Kirchhoff's law. So I understand where. So the 5.2 is definitely wrong. 3.2 probably is what the key, and it should have 10 minus 6 minus 8.2 on the key, right? On all of these. So what'd you get for VCE on all of them? If you did that, we probably messed every one of them. So this is the circuit right here, right? And what we're trying to do. So if I'd have gave you all that circuit in DC, you would have had what? No problem with it. It's the same circuit. It's just that it's drawn a little different. We don't see circuits like this anymore. What we see is circuits that's related to either circuit common or circuit ground, right? And what this does is, people don't understand this either. That represents a wire, right? So that represents this wire right here. Well, what we do is we use a symbol to represent a wire, and it makes our what? It makes our schematics less cluttered. So that's that symbol right there. And like I said, I've heard it, I don't know how many times where people don't hook it up and they say, well, I thought it was hooked up in the trainer. And they'll have a resistor out there with nothing hooked up. They'll have something hooked up to one side and nothing hooked up, and they think it comes from the trainer automatically. Well, what do we call these capacitors right here? These capacitors right here have a name. That's the type of capacitors are, but they have a name in a transistor circuit. So what do they let us do? Well, they let us couple an AC signal into a DC bias. We call these coupling capacitors. What's that? Well, then I did it wrong. What did I subtract? Yeah. Well, I did it wrong. Really? Yeah.
You didn't add the team on the
I just probably used the wrong value for VC. VC is, where's VC at? Right here. So we're not subtracting 10, we're subtracting 6. So VC equals VCC. VC equals VRC minus RC. So let's figure out what we're doing wrong here. Oh, I know what I'm doing. I know what I did. I mean, I erased it, unfortunately, but no, I didn't. It's up here somewhere. Okay. So what I did is I wrote it down wrong. It's right. Both of them are right. So let's go back and look at this. So that's a good point. So what did we get for VR3? Okay, 4 volts. 3.9, okay. What did we get for, which means VC would be equal to 10 minus 4. VC would be equal to 6. Okay. Now, then we had VR4 was equal to what? So we just used the wrong numbers. Is equal to 800 millivolts. So if we did it before, and that's why I wrote down the 4, and then I got totally confused. So this guy's dropping 4 volts. This guy we don't know. This guy is dropping 800 millivolts. So we just got ourselves confused. This is 10 volts. So I wrote down 4, but for some reason I changed my mind, or y'all told me or something like that. I don't remember what happened. So VCE would be equal to 10 minus 4 minus 0.8. Or 800 millivolts. Y'all understand? So a while ago, somehow I stuck 6 in here and not 4. Or, we know we have 6 volts right here, and we know we have 800 millivolts right there. So what would we get if we subtracted it out using full Kirchhoff's law? Should get 5.2, right? So 5.2 is the right answer. Or, I can take this voltage here, which is 6 volts, and that voltage there, which is 8 volts. So voltage collector to emitter could be equal to 10 minus, would be equal to, I'm fixing to do it again, would be equal to 6. This voltage, so it's a difference in potential, right? What do I have sitting right there? Wait. Okay. So what do I have sitting right here? Relative to common. So if I took a meter and I measured right there relative to common, what would it measure? It would measure 6 volts. If I came over here and measured this relative to common, it would measure 800 millivolts. So it's up to you which way you use. This is the one I started off with, but I started off with 4 and then wrote 6. I don't know if y'all said something and I agreed with you or not. Or it could be 6 minus 0.8. Either or, right? So we could use BR3. We could use we could use VCC minus BR3 minus BR4. That would be one formula, right? You understand? Or we could use what? We could use voltage collector to emitter would be equal to VC minus VE, which is what the formula tells you. We call it VCE, right? You understand? So it says, okay, if I use this as my common, and then I come over and do that, what would it measure? We're just going to measure 5.2 volts. So this tells you what to subtract, right? So this tells you to take what? VC minus VE. That's what that voltage collector to emitter tells you. But either one of them will wash. Will work. Whether you use Kirchhoff's law or not. So you can see what I did when I first wrote it down. I put 4, but then I came back and changed it to what? 6 for some reason. Tell my worksheet's right. Yeah, so when you said all of them's wrong, that kind of, one of them might have been wrong, but there's no way in the world I'd have made that mistake 4 times. So anymore, they all work what? Exactly the same. So it's just 4 different circuits that have different voltage gains, right? But every one of them give us a voltage gain. So if they give us a voltage gain, and we hadn't figured output, these are all unloaded, right? You understand that? Just to get a feel. If I load this thing, and it would be worthless for me to have an amplifier that don't run a load. So what happens if we load this thing? What should happen to the gain if we load it? Should it go up or go down? So what happens to a battery? So if you got a battery and you measure 1.6 volts across the battery, which is what they usually measure if they're unloaded, what happens when you put a light bulb across that? Is it going to go up or is it going to go down? Yeah, so the voltage goes down just strictly because of the internal resistance of the battery. It don't have much, but it's got some, right? You understand. So that's why you go out here on your car and you measure across not with your engine running, you put your voltmeter out there on your battery and you turn your lights on, what's going to happen to the voltage? It's going to go down, right? So what should happen to the voltage gain of this amplifier if we put a load out? It's going to go down. The voltage gain is going to go down. And so the actual formula So if we come here and load this down with a 10K resistor, then we wouldn't use this guy here. We'd use these two right here in parallel to figure out what the load would be. Right? You understand that? So what would it be? So I'd say R out. We call this R out, which would be, you can use the product over the sum, or you can use the sums of the reciprocals, whichever one you want. So the product would be 1K times 10K over the sum. You're about to use parentheses down here, which would be 1K plus 10K. Or you can use, so when you only got two resistors, you can use what we call the product over the sum, which means you multiply them together and then you divide them by their sum. Or you can use the formula that most people use in DC, and that's the reciprocal of the sums of the reciprocals, right? Oops. So we can use that formula right there, or we could use 1 over 1K plus 1 over 10K. I know it's going to be less than 1K, right? About a little over 900. So that means our gain dropped way, way down. So what do we get here? The bar out would be equal to what? What's that? Which means we get a gain of, instead of 1K over 200 ohms, it'd be 910 over 200. Our gain would be 4.7, but we saw it drop down, right?
Yep.
So the actual formula is R out over R in. We're going to change that a little bit later on to show you how we sure enough get some gain out of these guys. Are you okay? Now that's not going to be on the test. The ones that's going to be on the test is going to be one of these off this lab. So if y'all, off this worksheet. So if you do okay on the worksheet, you shouldn't have any problem with the circuit off the test. So it's going to be unloaded. So what we usually do is we usually learn how to calculate them unloaded, and then we come back and load them, and then we're going to do something with R4 cause the gain just to go out of this world. The voltage gain. We're going to sacrifice something. We don't ever get something for nothing, right? You understand? We'll have to sacrifice something. So any more y'all want to work? Huh? Well, we're going to, of course, we'll throw a few little curves in it on next class, but we're not going to worry about today. What I want y'all to do, I know y'all, we're going to have to go lab, guys. I don't know what these other guys are going to do. I know Melton sent me a text saying he had to take his kid to school because his kid, they delayed all the Jefferson County school for 2 hours for some reason. And I think one of the community colleges delayed their classes by 2 hours. You know. Are we okay? Y'all can vote today, right?
Yeah.
Huh?
Yeah.
I didn't ask who you voting for.